Hello class, so let's start with the explanation of some of these problems for the stage 3 for Mastering Physics. There are 11 problems and I'm going to be solving either 5 or 6 of them. So the most difficult ones, of course. So let's see, the first one is quite easy. Then this second one, I believe this one I already performed with you in class, but anyways, I'm gonna do it again one more time. What do we have in here? We have the following. We have, let me see if the recording is actually going on. Okay, perfect. We have a helicopter of this much mass. So let's write down the mass of the helicopter over here. So we have a helicopter. This is the mass of the helicopter. And it's ascending from the ground with an acceleration of 3.5 meters per second squared. It's ascending upwards with this acceleration, 3.50 meters per second squared. And that's, I mean, basically this is the helicopter, right? And it's going upwards, it's going in this direction. Okay, so that's the whole context. The part A is asking you, over a 6.5 seconds interval, what is the work done by the lifting force? Okay, this is what may be troubling you a little bit. This thing about the lifting force. What is that? Okay, you must realize the following, guys. When the helicopter is going up, there are basically two forces acting on the helicopter at the same time. There is one force directed upwards that I'm going to call FL, and the L means lifting force. And there's another force, which is basically the weight of the helicopter, right? Because every single object has weight, which is the force with which Earth pulls from any object on its surface. So we have lifting force going upwards and the weight going downwards. And these are all the forces acting on the helicopter right now as it ascends with this acceleration. Okay, so that's what we mean by the lifting force. Now, we have the mass of the helicopter and we have the acceleration of the helicopter. And when you look at Newton's second law of motion, that law tells you the following, that force equals mass times acceleration, right? But you need to understand this, guys. This force is actually the sum. This F right here is actually the sum of all the forces acting on the helicopter. Okay, or any other object. This is the sum of all forces. Now in here, how many forces do we have acting on the helicopter? Like I said, we have two, lifting force and weight, and therefore we can replace this F, which is the sum of forces, with these two. And I'm going to do it in this way. The lifting force minus the weight equals mass times acceleration. Why did I put the weight as a negative quantity? Or, yeah, as a negative quantity. The reason, guys, is that forces sum like vectors, and the ones pointing downwards should be taken as negative. Okay, so do we know the weight of the helicopter? Yeah, because we can calculate it. The weight of the helicopter is going to be its mass times gravity. Therefore, the weight is going to be this much mass times gravity, like that. And let's actually calculate that value. You're going to be using your calculator a lot, so have it there, please. Okay, this is going to be 7,644 newtons. So let me input that in here. 7,644 newtons. That's equal to the mass of the helicopter, one more time, times its acceleration, which I'm told is this much, 3.50 meters per second squared. So let's actually calculate this value again, and let's put this value in the other side of the equation. Let's add it. So let me calculate this value first. gonna be 780 times 3.5. I get 2,730 newtons, and then plus this much once I add it to both sides of the equation. So we get that the lifting force is these two quantities, and I get 10,374 newtons. So this is the lifting force, guys. This is the lifting force. Okay, and the question is this: over a 6.5 seconds interval, what is going to be the work done by the lifting force? So we have the lifting force, and if I want to calculate the work done by the lifting force, I need to know the lifting force. I need to know the displacement of the helicopter over this interval of time, and the cosine of the angle, right? Now it's clear that the lifting force and the displacement of the helicopter, which is also going upwards, it's clear that they are in the same direction. Therefore, the cosine of theta is going to be the same as this. Cosine of 0 degrees, and cosine of 0 is just 1. So basically this whole equation reduces to this. So basically the work is going to be equal to the lifting force, which we already have, 10,374 newtons, times the displacement. And we don't know the displacement, right? We don't know the displacement of the helicopter, but we can find it. And the way to find it is through this equation, guys. The displacement is going to be 1/2 of the acceleration times the time squared. This is a formula that we haven't seen. Let's just use it in order to calculate the displacement. So it's going to be 1/2 times the acceleration of the helicopter, which is 3.5, times the time, which is 6.5, to the square. Don't forget the square. So it's going to be 73.93 meters. That's going to be the displacement. So let me go back here to my formula. We have the displacement here, so I'm going to put it right there, 73.93 meters. And that's how you can calculate the work done. Just multiply these two things, and we get 767,027.62 joules. So this is the first of my solutions, guys. Of course, you're gonna have different numbers, right? So you have to do something. You have to input your own data in order to find this value right here. So that's how you find it. There it is. This is the answer that should go here. Okay. Now, the next question is, what is the work done by the gravitational force? By the gravitational force. Let me erase this part. And what they mean by that, guys, it's basically the work done by the weight of the helicopter, because the weight is the same as the gravitational force. So the work in, let me write here part B so that you don't get confused. Part B, we want to calculate the work done by the gravitational force, and in order to do that, you need the force, which is the weight. I'm going to put in here the weight of the helicopter times the displacement times the cosine of the angle between this force and this displacement. So what do we get? The work will be the weight, which is this much, 7,644 newtons. The displacement, which we already got, it's this much. I'm gonna put it there again, 73.93 meters, times the cosine of the angle between the weight and the displacement. Look at them. The weight goes downwards, the displacement goes upwards, and so between these two vectors, guys, there is an angle of 180 degrees. There you have it. And that's how you calculate the work for the part B. This number times the cosine of 180, you're gonna get a negative result in here. Make sure of that. You have to get a negative result. Okay, that's how you solve part B. I told you I'm not gonna be doing the whole thing. I'm just gonna give you the explanation, right? And what is the work done by the net force on the helicopter? And that's what I was telling you at the beginning, right? It's this part. When you use this second law of motion, this F represents the net force. The net force, guys, is basically the sum of all the forces acting on a particle. So in this case, my particle is a helicopter, and there are two forces, right? This and this, and the net sum of these two is basically the following. Let me write Fn for net force. The meaning of the word net means total, and that's going to be equal to the lifting force minus the weight. Remember, why minus? Because it's opposite to the lifting force. And that's how you get, oh, do we have this thing? Yes, we have it. Do we have the weight? Yes, we have it. So now you can calculate the net force. You see? So this thing is already understood. And if you want to calculate the work done by the net force, then all you need to do is part C, the work done by the net force is going to be equal to the net force, which is already obtained, times the displacement, times the cosine of the angle between the net force and the displacement. And clearly the net force is going to be going upwards too. It's going to be in the same direction as the displacement, because if the net force was not in that direction, the helicopter would not be ascending, right? So this and this go in the same direction, therefore this angle theta will be actually 0 degrees. So that's it. That's how you calculate this part C. Input this value here, which is FL minus W minus the weight. Calculate that, put it there, put the displacement, multiply times cosine of 0 degrees, and you get the work for the part C. And that's how you solve problem number 2. Okay, let's keep on moving. Okay, this one. We have 1500 kilograms automobile travels at 75 kilometers per hour. What is its kinetic energy? So remember, guys, in order to calculate these type of things, you need to use official units. Official SI units. Official units of the international system, which is the meter, the kilogram, and the second. Always, if you're not given those units in your quantities, you need to transform. For example, this 75 kilometers per hour, I'm going to be transforming that into meters per second. And let me do the conversion. It's very simple. That's 20. Wait a minute. 28, I'm sorry. No, it's 20. 20.8. 20.83 meters per second. That's the first thing you got to do, guys. So what is its kinetic energy? What is the kinetic energy of this car with this mass going at this velocity, which is this velocity? Remember, we're going to use this velocity in meters per second. So kinetic energy is equal to 1/2 of the mass times the velocity squared. Therefore, the kinetic energy is 1/2 of the mass of the car, which is 1500 kilograms, times the velocity of the car, which is 20.83 meters per second. And you multiply all of this, and you're gonna get your answer in joules, and you're gonna put it there. That's it, guys. That's the part A. Now for the part B, we are told what net work would be required to bring it to a stop. Okay, so in order to solve that, guys, what you need to consider is this. Let's actually calculate this number. I want to calculate this number. it's going to be 0.5 times 1500 times 20.83. I was forgetting the square. You know, it's very easy to get confused. We're gonna get the following. We're gonna get 325,416 joules. Okay, and basically, guys, remember, the work is the same as energy. The work is the same as energy. So if you have the following, at some point you have the car over here with this much energy. At this point, when the car is going at this velocity, the car has this much energy, 325,416 joules. And basically, guys, what you need to do is take that energy away from the car in order to stop it. Okay, imagine the car is going from left to right. The car is going in this direction. Okay, so basically, what do you need to do in order to stop it? You need to apply a force in that direction, right? You need to do work on that direction on the car in order so that it eventually stops. Let's suppose it stops right here. The car is already at rest right here. So the car will have no kinetic energy at all. It's going to go from this much energy to 0 joules of energy. And therefore, guys, the reasoning is this. How much work do you need to apply on the car in order to subtract all of this energy from it? You need to apply as much energy as it had in the beginning, because work is the same as energy. So if the car has this much kinetic energy, you need to apply work of the same order. This much work on the car in order to make it stop. You see, so basically it's going to be the same as this the same as this result. Okay, it's going to be here. Either by the way, if you enter this value here and it doesn't accept it, try negative. Try both positive and negative values, and one of those has to be accepted for sure. Okay, so that solves the problem number 3. So we have already 2 down. Let's go to the next problem. Problem number 4. We have the following. It's just one question. It says, if the work required to speed up a car from 15 kilometers per hour to 23 kilometers per hour is this much work, let me write that down. 9 times 10 to the 3 joules, 9,000 joules. What would be the work required to increase the car's speed from 23 kilometers per hour to 35 kilometers per hour? Okay, this one seems like a difficult problem. Let's see. So we need this much work in order to speed up the car from this velocity to this velocity. Okay, so once again, guys, we need to transform these velocities, this velocity and this velocity, into meters per second. This is the initial velocity. I want to transform it, and this is the final velocity of the car, and I want to transform it. So let's do that. 15 kilometers per hour is the same as 4.16 meters per second. This one is going to be 6.38 meters per second. So the car is going to go from this velocity to this velocity by the application of some work. Basically, what you have is this, guys. You have the car right here. It's going at this velocity at the beginning, and then somebody applies work on the car, and therefore, since it's applying work, it's going to provide energy to the car. And then at some time later, once this much work has been performed, then this car will be still traveling to the right, but now with this much velocity. Okay, so that's basically the first part of the problem. Now let's calculate the kinetic energy that the car has at this point, guys. The kinetic energy that the car has at this point. So at this point, it would be 1/2 times its mass, which we don't have. Can you see? We don't have that mass. And we do have its velocity, which is 4.16 to the square. So let's calculate all of this. Even though we don't have the mass, what I mean by calculating all of this is basically multiplying 1/2 times this number to the square. That's all I need you to calculate. You're gonna see how this one works. So we get 8.65 m times m, because remember we still have this variable, and let's call that Ki for initial kinetic energy. And then right here, when the car is going at this speed, let's calculate that final kinetic energy. So that final kinetic energy is still going to be 1/2 times its mass times its final velocity to the square, which is 6.38 to the square. Let's calculate this times this. And you get 20.35 meter. I'm sorry, it's not meters, it's joules. Joules and joules. Okay, guys. So basically, what's happening right here? The car is going from this initial kinetic energy to this final kinetic energy, and no, wait, I'm sorry. I should write the m. I'm sorry, guys. That m was not from meters. It was from the mass. I was getting confused. 8.65 times the mass, joules, and in here it's 20.35 times the mass, joules. I was getting so confused. Okay, and the difference, guys, between this kinetic energy and this kinetic energy should be the amount of work provided to the car. Because remember, the car went from this velocity to this velocity by the application of some work, which is this much. And therefore, the difference in kinetic energy from this kinetic energy to the next kinetic energy should be the same as this. So basically, the difference between the final kinetic energy minus initial kinetic energy should be equal to this number, which is 9,000 joules. And you're gonna see what this equation allows me to find. Let me write Kf in here. Kf is this much, 20.35 times the mass. You see, this m is mass. It's not a unit. It's the m of the mass of the car, and minus the initial kinetic energy, which is 8.65 times the mass, equals 9,000. And as you can see, we have an equation which is one variable, which is the mass. So let's solve it. We're gonna get the following. We're gonna get that the mass is equal to 769.2 kilograms, which is okay for a car, right? I mean, we know that cars are somewhere around this many kilograms, about 800 kilograms or something. So this is the mass of the car, guys. We have discovered the mass of the car. Why is that important? You might be asking. Well, that was important in order to solve the actual question, which is this. What would be the work required to increase the car's speed from this much to this much? So let's just keep this value. That's the only thing we need. So I'm gonna write it. I'm gonna erase the whole everything. Basically, all of this analysis was done in order to obtain the mass of the car, which is 769 kilograms approximately. And let me put it right here. The mass of the car is this much. 769.2 kilograms. That's the mass of the car. And I can erase the rest of it. Okay, and now like I said, the question is, what would be the work required to increase the car's speed from 23 kilometers per hour to 35 kilometers per hour? You're gonna do something similar, guys. Basically, you're gonna put these two velocities, this initial and final velocity, transform them into meters per second. You're gonna get 6.38, just as before, right? Because it's the same as in here. And now 35 is gonna be 9.72 meters per second. So basically, this work will be the one required to increase the car from this velocity to this velocity, or in other words, to increase the kinetic energy of the car from this kinetic energy this is the first kinetic energy that the car will have when it's going at this velocity. I'm ignoring the units on purpose in order to simplify this thing. So let's calculate the initial kinetic energy of the car. We're gonna get 2,453.7 joules. Now I'm still forgetting the square here. This is wrong. Let me do it one more time. 0.5 times 769.2 times 6.38 to the square. This is going to be 15,654.9 joules. Okay, that is the kinetic energy of this is the kinetic energy of the car that is going at this velocity when it's going at this velocity. Now the final kinetic energy of the car will be the one when we use this final velocity. It's going to be pretty much the same. 1/2 times the mass of the car times the final velocity of the car to the square. I'm ignoring the units. Let's calculate all of this value, guys. We're going to get 36,336.39 joules. You see? And so we have an initial kinetic energy and a final kinetic energy when the car goes from this initial velocity to this final velocity. So there's a change in the kinetic energy of the car, clearly, right? Because it's going faster. So it obviously has to increase its kinetic energy. And the question is, what would be the work required? What would be the work that you have to apply on the car in order to make it go, or in order to change its kinetic energy from this much to this much? Well, since work is the same as kinetic and as energy, all you need to do is subtract this value from this value. It's this minus this, and that's going to be the amount of work required in order to change the kinetic energy from this value to this value. You see? That's it, guys. It's that simple. It's about, it's going to be about 20,000. Let me make the calculation. It's going to be, yeah, about well, I get the following. The work is going to be 20,682 joules. That's the figure I'm getting. That's the value that should be here. Okay, so that's problem 4 for you guys. That solves problem number 4. Okay. Problem number 5. This one is very simple. Problem number 6. This one also is quite doable for you. Should be. Okay, let me do this one, problem 7. Let me make a little stop. Okay guys, so problem 7 out of 11. This one is rather also quite simple. So we have this. We have a 0.3 kilogram ball that is thrown vertically upward with an initial speed of 13 meters per second. That is the whole context. And then the question is this: what is the maximum height reached by the ball? So let's see. So we have the ground, okay, and let's suppose that this ball is being thrown upwards from ground level. Like the ball is right here, and somebody just, I don't know, kicks the ball upwards or something. In some way the ball is being thrown upwards by a foot or a hand. We don't care about that. We don't care about the way. Okay, so it's gonna be thrown upwards. Clearly the ball will reach a maximum height, which I'm gonna suppose it's here. This is the max height h, let's call it h, and it's gonna go backwards. Okay, so they asked me what's gonna be this maximum height, what's gonna be h. Let's find h. Okay guys, this is a problem on conservation of energy. Conservation of energy, which means energy is not created nor destroyed, it's only transformed. So let's see guys, when you have to analyze this motion at 2 steps or at 2 different points. This point right when the ball is being kicked or thrown, right when the ball is at ground level. Let's call that initial point. And right when the ball reaches its maximum height, which is at h. Right here, this is the final point of the motion. And the key question guys is this: what's the total energy that the ball has at this point initial, at this point I? What is the total energy that it has? Let me put that in blue. The total energy guys that the ball has at this point is just kinetic energy. Why only kinetic energy? Because it's just been thrown with this speed, you see? So it already has kinetic energy due to motion because it's being thrown upwards. Now, does it have kinetic energy? No, because it's pretty much at ground level. So the amount of the amount of potential energy is 0 joules, and the amount of kinetic energy can be calculated. How? Well, we know the formula for kinetic energy, right? It's 1/2 times the mass times the velocity squared, and therefore I can calculate the kinetic energy with which the ball starts going upward. So it's going to be 1/2 times its mass, which is 0.3 kilograms. Everything is in standard units, so that's good. And the velocity is 13 meters per second. So it's 13 meters per second to the square. Remember, you can, if you know that you're using official units, you can ignore the units at this point. I believe it's a good suggestion in order to keep the calculations clean. Okay, so let's calculate all of this. 1/2 times this number times the other number to the square. So we're gonna get the following. I'm getting 25.35 joules. This is the kinetic energy that the ball has at this point, right at the beginning of its motion. Right at the beginning, right when it's thrown. Okay? And then the ball is gonna fly upwards, fly. It's gonna slow down, and it's gonna eventually stop right here. And then it's gonna come back. Okay, then what happened? What is happening? How can we analyze what's happening when it's going upwards? Well, what's happening is that it's losing kinetic energy. It loses kinetic energy, right? Because this velocity with which it started is going to diminish, right? So it's going to lose kinetic energy but it's going to gain potential energy. Why? Because obviously the ball is gonna reach a greater height, and you know that the greater the height, the more potential energy a particle has. So it loses kinetic energy, but it's gonna gain the same in potential energy. You see my point? Whatever energy loses in kinetic energy, that's the same amount that the ball will gain in potential energy. You see my point? If it loses minus 5 joules of kinetic energy, then it's gonna gain 5 joules of potential energy, so that the balance is 0. You see what I mean? The balance of losses against gains is gonna be 0. That's how it works, guys. I want to erase it. So pretty much the whole point is this: when the ball reaches its highest height, its greatest height, then at this point the kinetic energy of the ball is 0. This much energy, which was at the beginning, will be 0 at this point. At this point the K will be 0, but the potential energy will be the same as the initial kinetic energy at that point. You see, so to wrap it up, the initial kinetic energy of the ball will be transferred completely to potential energy at the greatest height. So this is the number that should be right. No, I'm sorry. That is the potential energy at the top of the motion. And now that I know that potential energy, I can use the formula for potential energy, which is this, remember? And then I can input that value in here, 20.35 joules, and then this M stands for the mass of the ball, which is 0.3 kilograms. And you know what G means, 9.8 meters per second squared, and H is the only variable in this equation. That's it, guys. Number equals number times variable. Isolate the variable H, and that's the one you should be putting right here in order to get a correct answer. So that's problem number 7 for you. Okay, now this one. Okay, again, this one is doable. It's pretty much about the same idea I said in the past problem. So you can do 8 on your own. What about number 9? Okay, let's do this one, guys. Let's do this one. We have a race car of this much mass. So let's put the highway, let's put the car. We know the mass of the car, which is 1300 kilograms. There you go. And this car can go from 0 to 90 kilometers per hour in 5.5 seconds. So we know the initial velocity, which is 0 meters per second, and the final velocity is 90 kilometers per hour. And let's convert that to meters per second very quickly. And you get 25. So this car can go from 0 to 25 meters per second in how much time? In 5.5 seconds. Okay, this is all we know. And then the question is this: what average power is required to do this? ¿Cuál es la potencia promedio requerida para hacer esto? Remember that power is translated as potencia. So what is the definition of power? Is work over the amount of time in which this work is done on certain particle. Okay, so do I have the time already? Yes, it's 5.5 seconds. So all I need to do is the amount of work that needs to be done on this car in order to make it go from this much velocity to this much velocity. Okay, So basically, once again, I'm gonna do it in blue. If I have the initial velocity, guys, I can calculate the initial kinetic energy of the car, which is gonna be zero joules. That's clear. Why? Because I mean, it doesn't have any kinetic energy. It's at rest. Because it's at 0 meters per second. It's not doing anything yet. And the final kinetic energy of the car will be 1/2 times its mass, which is this much, times its final velocity to the square. So let's calculate the final kinetic energy. It's the calculation of all of those things. And you're gonna get 406,250 joules. So the car will go from this initial kinetic energy to this final kinetic energy by the application of some work. And since work is the same as energy, then in order to make the car go from this initial kinetic energy to this final kinetic energy, you need to apply the same work, which is this much, the same amount of joules as work. So it's going to be this much. Let me go back to yellow. It's going to be equal to 406,250 joules over this much time, 5.5 seconds. And that's it, guys. You perform this calculation and you get the average power that should be placed in here for a correct answer. And that solves problem 9. It was quite simple. Problem 10. Okay, let's do this one. Okay, what are we having here? We have a pump, una bomba. A pump lifts 280 kilograms of water per hour to a height of 3 meters. Okay. So let's try to more or less draw that thing. So, I mean, you have some water over here. You maybe have a river or something. And you have a pump, una bomba. And this pump is going to pump water to a height of 3 meters. Okay. And it's going to pump this much water, guys. 280 kilograms of water per hour. And it's going to lift water to a height of 3 meters every hour. How much water? 280 kilograms of water. So you may think of this as, you have a certain package of water, and that package has a mass of 280 kilograms of water, and then over 1 hour, which is 60 minutes, right? Or 3,600 seconds. Remember, we need to convert it to seconds. So this pump is gonna bring this mass of water to this height, 3 meters, every hour. It's gonna put 280 kilograms of mass of water to this distance every 3,600 seconds. That's what the pump is doing. Okay, so what? What's up with that? Well, let's see. What is the minimum necessary power output rating of the water pump in watts? Okay, basically, this is a very fancy way, guys, to ask about the power delivered. The power delivered by the pump. This is what we want to answer, because basically, guys, the pump, by lifting this mass of water to a certain height, it's doing work on such mass of water. It's doing work. Basically, the pump is just lifting this package of water, which with this mass to this height, and that's all it's doing, guys. That's all it's doing. Now, how much work? Remember, what is power? Power. Let me go back to blue. Power is work over time. We already have the time, which is this many seconds. So it's work over 3600 seconds. Okay, and so we need only to calculate the work done by the pump when lifting, once again, this much water to a height of 3 meters. Okay, once again, guys, remember, work is the same as energy. When we do work on a particle, we are giving it energy. You see, that's basically the whole thing. That's the whole rationale. When this pump is doing work on the package in order to lift it, right? Because obviously the pump has to apply a force, right? It's doing work on the package, and it's gonna give it energy. Now, what is the potential energy, guys, of this package of water once it's being lifted at 3 meters? Once this package of water is 3 meters from the ground, what's its potential energy? Well, let's calculate that. It's gonna be the mass times g times the height. So what is the mass? 280 kilograms. What is g? 9.8 meters per second squared, and height is 3 meters. So let's calculate that potential energy. Let's calculate the multiplication of those three numbers. We're gonna get, I'm getting 8,232 joules. So listen, guys, listen. The package of water went from this point here, which is basically having a potential energy of 0 joules, because when something is at ground level, then that something doesn't have potential energy with respect to that level. So this package of water went from this much potential energy to this much potential energy once it was lifted. So you see, what is the net change in energy? It's this much. By doing work on this package of water, I gave the package this much energy, guys, 8,232 joules. And so, therefore, that was the same amount of work that that the pump performed on the package. This much energy, guys, this much work. So this work is the same. It's gonna be 8,232 joules over this many seconds, and this number, whatever it is, that's gonna be the power that should be here. Okay, and then finally, this part B, what is the minimum necessary power output rating of the water pump in horsepower? Well, that's quite simple. All you need to do is this. Well, let me actually calculate this value here. What value do we get out of this? We're gonna get 2.28 joules. I'm sorry, 2.28 watts. Remember that the unit of power is watts. So 2.28 watts. So this is the power, guys. This is the value that should be written right here. And now, all you need to do in order to answer B is the same question. Part A and Part B are the same question. The only difference is the unit. In the first place, it was in watts. Can you see? And in the second place, it's in horsepower. So all you need to do is to transform this many watts, 2.28 watts, into its corresponding number of horsepower. Horsepower is just another unit for power. That's it, guys. It's nothing more complicated than that. It's just another unit. Just like when we have miles and kilometers, these two units measure the same thing. They measure length. These are different units to measure length. This and these are different units to measure power. And all you need to do is a conversion from this watts to some horsepower, and put that value, this value, in here, and you're set. Okay, so that was problem 10 for you. That was problem 10. And I believe that's it, guys, because the next problem, except an electric motor. Well, no, I need to cancel this one too because we haven't seen anything about efficiency. Let me cancel this problem, guys. And that's it, guys. There will be just 10 problems. I solved 6 for you. As you could see, in some cases I did not perform the calculations because it's pointless since you have other numbers, but I provided to you the general explanation. So there it is, guys. Thanks so much.